Okay, let's continue. By the way, you may have noticed our lectures are being recorded on video. This is part of the OpenCourseWare project. So they are going to be also available to you on a website. So if you miss a lecture, you'll be able to listen to it online. Okay, but I mean, there's going to be a time lag. I mean, you don't expect the video to appear on, they need to process the video before putting it online. So for example, if just before the midterm, the week before midterm may not be available if you missed that lecture. But probably the first lectures, the first month's lectures are going to be available probably before the midterm. Okay, so let's start talking about our PlaneSleep algorithm. For the line segment intersection problem, the first observation to speed things up is basically if two line segments, they're far away. If you know that they're already far away, there's no need to test for intersection, right? I mean, and what does far away mean? For example, if we can look at their x coordinates, their extents of their projections on the x-axis. If their projections on the x-axis do not overlap, it's impossible for these two line segments to intersect, right? So one way to speed things up is that, again, we can sort their endpoints in terms of their x coordinates and start processing these points from left to right. And when we come to an endpoint of a line segment, we may maintain a list, for example, like the current lines, a set of current lines that that intersect this x is equal to I, for example, vertical line. So we are going to sweep a vertical line from left to right, and during the sweep we are going to maintain a list, a set of line segments that intersect this vertical line. So, and when, for example, when we come to a beginning point of a line during this sweep from left to right, we are going to insert this line segment to the set of line segments that intersect it, the sweep line. And if we come to an end point of a line segment, we are going to remove it from this set. So whenever we encounter a new line, okay, so when we encounter a new line, meaning that our vertical line during the sweep hits the beginning point of this line. At this point, all I need to do is check whether this line segment is intersecting with the current set of line segments that intersect this vertical line. In other words, for example, if there was a line segment which lies here, it's going to, since we have encountered its endpoint before coming to here, we are going to remove it from our current set of line segments that intersect this sweep line. And we are going to only have things here which are going to be intersecting the sweep line, whose endpoints are before this x is equal to I point. Okay, at this point, when I encounter a new line segment, the current set of lines that intersect the sweep line are the lines whose beginning endpoints are to the left of this vertical line and whose right endpoints are to the right of this vertical line. So this is what I maintain during this sweep. And all I need to do is to check whether there's an intersection or not. All I need to do is whether this new line intersect these set of lines that intersect my sweep line. So if such an algorithm is going to guarantee to you that you're only going to be checking intersection between line segments whose x-axis projections overlap. Okay, if their projections on the x-axis do not overlap, these two lines are never going to be on the same set of current line segments during the sweep. Okay, so what you guarantee is you are going to do the check between line segments whose x-axes overlap. For example, you may say that, okay, I check this new line with the already existing ones. What about a situation like this? Okay, sorry, I'm going to use a different color. So at this point, their x-axes also overlap, but when I was doing the check for this line, this one was not on this list since I didn't come to its beginning point yet, so I didn't check whether these two intersect or not. So is my algorithm incorrect? No, because since this check, the intersection between these two checks are going to be done when you encounter the beginning point of the second line segment. Because when you come to the beginning point of the second line segment, it's going to be guaranteed that this line is still on the list because its end point is to the right of this beginning point of the yellow line. If it's not to the right of the yellow line, it means that it ends somewhere here. Their x-axis projections do not overlap and they cannot intersect anyway. Okay, so this is the main idea between the PlaneSleep algorithm. But the algorithm that I described right now, you can easily give me an instance in which all the x-axis projections of all the lines overlap. Still, there are only a small number of intersections. I mean, what if my lines are like this? Okay, if you can draw millions of lines like this, all of their x-axis projections overlap. And you may say that, okay, if I have something like this, after looking at this picture, I can say, okay, have the sweep line go from upper to down, just sort them on their y coordinates and do that. But what happens if I have lines that are on something like this? Okay, I have many lines. Either you sort them by x coordinate or y coordinate. Still, I mean. Actually, no, this is not a bad approach. I mean, if you sort them by their x coordinates, you're not going to test these lines with these lines. Actually, it's not a bad idea. But still, what we are looking for is an algorithm. Instead of looking at before looking at the picture manually and deciding whether to use to sort them by x or y coordinates, we are going to modify the original algorithm so that it's always going to guarantee to test for intersections that are potentially possible intersections. So even for this case, we are going to modify the algorithm so that we are not testing the intersection of this one with this one. So, okay, but now in the original, I mean the first x-axis projection overlap idea, now what we have is we have all the actually essential ingredients of a PlaneSleep algorithm. We have actually, I already used some certain terms that are part of a PlaneSleep algorithm, which is the sweep line, for example. What we have is a sweep line that we sweep the plane with the help of this line. And what happened was, when I was also talking about it, I said that I maintain a current set of line segments that intersect the sweep line. This is the status of a sweep line. During the sweep, I keep a status structure. This status structure was just simply a set of line segments that was intersecting the sweep line for this example. But we are going to see this set of line segments is not enough for efficiency. We are going to be using, in the modified version of the algorithm, we are going to be using a balanced binary search tree as the status structure of the sweep line. But those are the essential ingredients of a PlaneSleep algorithm. So we have a sweep line L. We are going to name this line as L, which we start from the leftmost point, for example, and go sweep the whole plane in a certain direction And during this sweep, we process our inputs. So the most important ingredient of a PlaneSleep algorithm is this sweep line. The second is the status structure of the sweep line. What is the status of the sweep line at a certain intermediate point? As status we mean, it may be the number of or the set of line segments intersecting the sweep line. That set is going to be our status, because the set of line segments intersecting the sweep line is going to be different when the sweep line is here, and it's going to be different when the sweep line is here. Okay? So that's the status of the sweep line. And also the other thing is this sweep. How are we going to make this sweep? What does it mean to sweep the plane? Am I going to increase this x coordinate 0.01, 0.01, 0.01? Go like this to sweep the whole plane? Obviously not, because we immediately observe that between certain things, for example, between this endpoint and this endpoint, when I'm sweeping the plane, nothing happens in the status structure. Okay? If you continuously sweep the plane using very small floating point numbers, this continuous sweep does not gain you anything. There's nothing that changes in your algorithm or in the number of lines that are intersecting. There's nothing that changes while you are between this point and this point. So this suggests us that instead of a continuous sweep, we can sweep the plane on discrete events, discrete points. So the only thing that changes is that at the end points of these line segments, when you see a beginning point of a line segment, you add it into the status structure. When you encounter the end point, the right end point of that line segment, you remove it from the status structure. So these end points of line segments are our event points. Okay, so that's the other critical ingredient of a PlaneSleep algorithm are these events. We have events, and these events are usually stored in a priority queue. Okay, it's stored in a queue. They're ordered. We have an ordered set of events. We know which event is going to come next. So if we have n line segments, we are going to have two times n events, and we are going to sort them by their x coordinate, and we are going to proceed from event to event in this queue. Okay, so those are the natural ingredients of a PlaneSleep algorithm. By using the same strategy, this PlaneSleep technique, you can find the closest pair of points given a set of n points. If somebody tells you find the closest in terms of distance, report me the closest pair of points in this set of n points. By using this PlaneSleep algorithm, you can report these closest pair in n log n time. And the actual time is actually spent on sorting the events. Okay, the majority of the time is just to sorting the endpoints. After you have sorted the endpoints, finding the closest pair is just on a linear scan over these points, you are going to be able to find the closest set of closest pairs of points on this line. But our problem is different, not closest pair problem. Our problem is finding a set of intersecting line segments. Now, obviously, the x-axis overlap observation was not enough for us to guarantee n log n complexity, because we just gave you a counter example saying that you may have all the x-axis of these line segments, x-axis projections may overlap. So we may need some other observation to speed things up. And that other observation is this. Instead of having, this became a messy figure, so let me just erase this part. And I'm going to start from scratch. Now, what if instead of having the status structure as a set of line segments, what if I order them with respect to their y coordinates when they intersect the sweep line? It's like this. If at the intermediate point in the sweep line, I have a set of line segments that intersect the sweep line. My original solution was just to use these lines 1, 2, 3, 4, 5, 6 just as a set, okay? No order in between them. Just they are in the set, and whenever I encounter a new line segment beginning with this endpoint, what I do is I just check with all the line segments in this set. But now, I need to ask this question. Do I really need to test the intersection of this with all the line segments here on this set? Maybe not, okay? So this observation that, I mean, it's a lemma in the book which says that if two line segments intersect at some point during this plane sweep, they become neighbors on this sweep line, okay? So it means that if you sort these points on their y coordinates, okay, if you have them sorted, all you need to do is when it comes here, okay, when something comes here, all you need to do is find this one and this one, make the check between these two, okay? But now we need to prove this lemma. I'm saying that, okay, can you give a counterexample in which there are two line segments that are intersecting, but they never become neighbors during the sweep line, on the study structure during this plane sweep? And actually the answer to that is no. I mean, there is no such case. I mean, the proof uses something like that. Imagine two lines are intersecting. Okay, two line segments are intersecting. And imagine they intersect at a point P. Now, what we assume is that, what we say is that at some point, and in the book, the plane sweep is from top to down, okay? But there is no, I mean, you can also do it from left to right. There is, the algorithms, this can be described similarly. So, the proof in the book actually did not convince me that well. So it's, maybe you could have a better proof. But what the proof says is that just imagine a line, a sweep line, just above this intersection point P. So that you select this line so that there are no other events between this dashed line and this point P. Okay? I mean, by just looking at this figure, you see that they are neighbors on this line L, right? I mean, the proof is by just looking at the picture. I mean, if they intersect at a point P like this, imagine a sweep line just slightly above this point P, you can see that there are no other things. And you select the sweep line so that there are no event points in this interval, okay? There are no event points in this interval. The sweep line is at that point. There are no events between the intersection point and this L1 and L2. Imagine a line L1 like this. So, obviously, these two segments are neighbors on L1, on this dashed line. They are neighbors, okay? There are no other events in between them. And at the beginning of the sweep, they weren't neighbors because the study structure was empty, okay? So in order to be neighbors, in order for them to be neighbors here, they have to be neighbors at some point in an event point above here, okay? So that's how the proof ends, okay? Let's say, okay, they have to, since they are neighbors here and they weren't neighbors at the beginning because the study structure was empty, there were nothing in the study structure, they have to be neighbors at some point. If they are neighbors in this dashed line, they have to be neighbors they have become neighbors at some point. And that's actually now I'm thinking it convinces me after I thinking it, because what we said is that our event points, between the event points, nothing changes. Okay, that's the main thing about event points. I mean, if there was an event point here like this, even if you jump directly from here to here, okay, it means that at this jump, before you jump to this point, there has to be they have to be neighbors. Otherwise, because if they were neighbors and they didn't become neighbors here when they intersect, for example, I mean, because we know that at this interval nothing changes. This is why we define discrete event points. Otherwise, we would have to do it continuously. If something was changing and can change between these intervals, we cannot do discrete events. We have to sweep the plane continuously. So it also violates our first assumption of having discrete event points being enough. So if we assume that they are enough, if we believe that discrete event points are enough, then we need to see that this dashed line, we see that in this dashed line they are neighbors. Okay? If in this dashed line they are neighbors, it means that there has to be some event point, a discrete event point on top of this dashed line that they are neighbors, because their neighborhood cannot change between this real event point and this dashed line. Otherwise, we would not be able to hop between these discrete event points. We would have to, if something changes in between them, we would have to do continuous sweep of the line. Okay, so the proof is like that. Now, so this tells us that they have to be neighbors at some point. So all we need to do is, when some new line, so this actually completes our algorithm. So all we need to do is, our study structure, instead of having as a set of line segments, we are going to have this study structure as an ordered set of line segments with respect to their y coordinates. But now the practical questions now arise. Okay. Which y coordinate are you talking about? Is it the beginning endpoint or end endpoint? Actually, I'm talking about the y coordinate that they intersect the sweep line. Okay, so they are going to be ordered in the way that they appear on this sweep line. So on this sweep line, by just looking at the sweep line, you can immediately, this gives a total order unless they intersect. Actually, even they intersect at this sweep line, but you can imagine just a tiny bit to the right of the sweep line. What will happen? Is this going to be on top, or this one is going to be? So you are going to order these line segments based on their intersection of their of the sweep line. Okay, on their y coordinates. So this is this part is the most difficult part in terms of practical implementation. This part, because what we are going to be in this balanced binary search tree, we are not having points, because these points change. The way, the place we intersect the sweep line changes as we sweep through the plane. We are actually having, as the book describes in a more abstract way, what the book says is that in this binary search tree, we have line segments. Okay, we are not having a single, or we don't have the intersection points. We just have the complete line segment on this balanced binary search tree. And this binary search tree gives us an ordering of these segments with respect to how they intersect the current sweep line. Now we may discuss actually it is possible to solve this problem. It's like all you need to do is define an ordering. Given two line segments, you need to be able to compare them. All we need to do is a comparison operator. Okay, if you're, for example, implementing this in Java, all you need to do is a class that implements comparable. Okay, so if you have a class that implements comparable, you need to define a comparator for these classes. You need to be able to compare two line segments. And this comparison, all we need to find out is that which line is greater than or equal to the other line. Given two line segments, we need to be able to define these operators based on where they intersect the sweep line. So maybe given two line segments, we also may need a pivot point, because for line segments like this, for example, if my lines are like this, the greater than are smaller to are very well defined, okay? If both endpoints of the one line is higher than the both endpoints of the other line, it's very well defined. Even for these, although this endpoint is smaller than this endpoint, I can still say that this line segment 1 is on top of, or is greater than line segment 2. So there's, again, the order between them is well defined in all places. So wherever you intersect these, line 1 is always going to be on top of line 2. Okay? The problem is, for line segments that intersects, line 1 and line 2, which one is on top of each other is not defined. Actually, it changes. To the left of this intersection point, line segment 1 is on top of line segment 2. To the right of this intersection point, line segment 2 is on top of line segment 1. So in order to have this comparison be defined, we need some pivot vertical line, okay? I mean, whether to the left of this, for example, I mean, we need such a pivot to do that. And that pivot is our sweep line, actually. And, or maybe we may say if they intersect, their intersection point may be the pivot line, because we know that we are already sweeping from left to right. All I need to know is that after I pass this point, their order is going to be changed. All I need to be able to compute is this pivot is their intersection, actually. So this can be implemented. An order between line segments according to their y coordinate can be defined by carefully thinking about these low-level issues. And your book does not discuss this, okay? They just say you are able to do this. You are able to sort these line segments based on how they intersect the sweep line. So they have a good figure, a tree that defines this. And we are going to use this tree to find when a new line segment enters this study structure. We are going to use this tree to find its left and right neighbors on this tree. So it's going to, when this thing, when this line segment enters this tree, it's going to have a certain position in the tree, and it's going to have a left and right neighbor on this tree, which indicates the immediate upper and immediate lower segments on this tree. So when a new segment enters, all I need to do is check whether segment 2 intersects with segment 1 and segment 3, okay? And also, you can immediately see that if I have an intersection like this, the order of line segments change. For example, if I have, now let me erase these, S1, S2, S3, S4. If I have these 4 line segments, before this sweep line, S3 and S4 were neighbors. So they were checked for intersection. However, at this intersection point, since the order of S2 and S3 changes, so this was S2, this was S4, now S4 and S2 became neighbors, and S1 and S3 became neighbors. So the neighborhood changes at intersection points. So whenever the neighborhood changes, I need to check for intersection, because I don't want to miss any intersection. And my main lemma says that if there's an intersection, they become neighbors at some point. So whenever I see new neighborhoods, I need to check for intersections. So what happens is that something changes. Since something changes at these intersection points, what do these points become? They become event points. Okay, so my event points are not just the endpoints of the line segments. Whenever I find an intersection, which can be towards the right of, so for example, after I check the intersection, I may find that, for example, at this point, when they become neighbors, this one became neighbors, I may find an intersection to the right of this sweep line. Actually, we are going to see that. Our main assumption is that we are also going to need to prove that if there's an intersection at this point of the sweep line, we assume that we have found all the intersections to the left of the sweep line. Okay? So when you find a new intersection at this point, it has to appear to the right of the sweep line. So some intersection point to the right of the sweep line is a future event point, which is going to be inserted into the event queue. Okay? So we cannot have a single static ordered set of events. So some events, like this intersection point, is going to cut in the queue, saying because its x coordinate is smaller than many event points that appear here. So we are going to insert this new intersection event to our priority queue. Yes?
We need the intersection points as start points for our sweep line because the start and end point may be sufficient to imply the intersection occurs somewhere in between.
Okay, very good. I mean, so when the order changes, maybe the intersection already occurred to the left of the sweep line. But in this example, as you are going to see, for example, between S1 and S3, the intersection is here. And the only place that they became neighbors may be after this event point. Okay, look at S1 and S3. I mean, this one and this one. They intersect, okay, but they become neighbors only at this intersection point. I mean, this S1 and S3, they may never be, I mean, there may, at the previous event points, they may never be neighbors. So we may, before coming to this intersection, S1 and S3 may never have been checked for intersection at all. So therefore, the only place that we are going to check for this intersection, I mean, maybe also there may also be no other event point before this intersection. Imagine all the other line segments are towards the right of this intersection. So there is no way, the only place that you are going to be able to detect this intersection is this intersection, which when they become neighbors. Okay, so yeah, I mean, intersections, I mean, because if you were looking, maybe you would say, instead of looking at the immediate neighbors, maybe looking at two neighbors ahead. I mean, we can increase this neighborhood of intersection check maybe to detect such things. But it's difficult to prove that it's going to work correctly. But if we introduce these intersection points as event points, this is the place where we check this intersection and we can guarantee we are going to find all the intersections. So the main reason the intersection points are added as event points is that because on the tree, the order of the segments change. The order that they intersect the sweep line is reversed. They are changed, so they become S3 become neighbor. At some point, S3 has to become neighbor with S1 because that was our lemma. If they intersect, at some point they need to become neighbors. And it is this intersection point that they become neighbors. So therefore we need to have these intersection points. And the only difficulty that having intersection points as events is that we need to have our event queue as not a static but a dynamic. Our event queue is also dynamic. We may be able to insert something in that, so it has to be like a heap. You can have a priority queue you can have a heap implementation of that. But the priority key is not the most difficult thing. The most difficult thing to implement in this algorithm is the status structure, which is the ordered line segments. Because the event queue contains only points. Okay, those points you can sort the points. Our events are intersection points or end points. They are just points. But in our study structure, we have line segments. Line segments are more difficult to compare with these operators compared to points. All right, so we have all the ingredients. I mean, we have all the preparations needed to write the algorithm now. But what we haven't thought, yes.
Is this algorithm for only finding two-line intersections?
No, all the intersections. Our goal is all the.
What happens when three lines are intersecting?
Yeah, that's a degeneracy. Okay, so I mean,
For example,
overlapping maybe.
are also overlapping.
So these are, that was, I was coming to that. I mean, we have covered this algorithm for general cases. This algorithm at this point reports all the intersections between all the line segments, but we haven't considered the degeneracies yet. Meaning degeneracies meaning that, for example, what if two line segments, for example, share the same endpoint? Are we going to consider endpoints as intersections? I mean, in other words, are these line segments closed line segments or open line segments? Do their endpoints included in the line segments? So this is, we can say if they say they're closed line segments, if they share endpoints, the shared endpoints are also going to be intersections. The other important thing is, what if three lines intersect at the same point, or three lines end at the same point, two lines end at the same point? So when you, for example, consider this, two lines beginning at the two line segments beginning at the same point. When you insert them into this queue, insert this binary structure, where are they going to appear? For example, this one becomes neighbor with this one becomes with neighbor this one. So we need to consider right slightly before to the right of the sweep line where they are going to be inserted. So at the same event point, we may be inserting two things. So in general, and also at a certain event point, we may be deleting three line segments simultaneously. Okay, so considering all these things, the algorithm needs to treat these as sets of line segments introduced into the sweep status structure, and sometimes a set of line segments can be deleted from the status structure at the same time. And also, if there are multiple lines intersecting at the same point, are we going to report this as a single intersection or intersection between all pairs of line segments? This is also output decision. We may say we are going to, since we are doing pairwise comparison between all, we can say we are going to report all the pairwise intersections, because finding the intersection point, I mean the same intersection point can be found by multiple lines intersecting at the same point, and the algorithm is going to handle that as well. The only thing the algorithm I described does not handle is what happens if two line segments overlap. I mean, they're on the same line. This is beginning and ending of one line segment. This is beginning and ending of the other line segment. So what happens? Their intersection point is they intersect at infinitely many points. Okay, so there are infinitely many points here. What are you going to report in this case? Are they intersecting where? Okay, so the algorithm the book describes does not handle such overlapping line segments, but it's given as an exercise. So it shouldn't be very difficult to handle these as well. But I'm not going to give you as an homework for this. Okay, so we are ready to describe the algorithm, but for your homework, we need to have another observation that is related to your homework, which is an intersection that is detected and put in the event queue at some point can be detected. The same intersection can be, I mean, for example, two line segments, they were neighbors. We tested them and we found an intersection. Okay, and assume that there are no degeneracies, no three lines intersecting at the same same point. Now, your homework will be, give us an example instance, geometric instance, any instance. Give an example in which the same event point is going to be detected twice. Okay, so can you give us a case? They are going to become neighbors again. Actually, I just found that this is a very simple example of since when you get into, while I was preparing for the class, I thought it was a difficult question, but since when you are into this algorithm so much, you can immediately see all these cases, and it's actually a very simple example. But I'm going to, so your homework will be, one of your homework questions will be to give a problem instance in which the same intersection, the same event point is detected twice. Okay, so in other words, two line segments become neighbors twice. When they weren't neighbors before, they became neighbors. Again, they weren't neighbors before, then they became neighbors. Okay, so I already given hints when during this description. And your other homework is going to be exercise 2.1 from the book, which is, let's see. Okay, so it's not related to line segment intersection, but it's about line segments. So given non-intersecting line segments along a horizontal slab, when I click on a certain point on this horizontal infinite, it goes to infinity in both hands. When I click on a certain point, I want you to give me a certain structure, certain binary search tree, which is going to find between which line segments this point is included in log n time. Okay, if I have n such line segments, they are not intersecting, so they partition this horizontal belt into, they partition them into non-intersecting regions. So what I want you to do is, when I click on a certain place on this belt, I want you to find out which line segments, between which line segments this point lies in very quickly. Okay, so think about, I mean, you can use trees, known structures like AVL trees. I mean, you can assume the existence of a balanced binary search tree. Okay, so this is exercise 2.1 from the book, and I'm going to also have these homeworks posted on the website. So you are going to have a PDF of this homework, okay? If you haven't taken notes right now, I'm going to do it. I'm going to post it tonight. Your homework is going to be posted tonight. And next week, I'm going to write the pseudocode. So we have made all the preparations for the line segment intersection algorithm, but I haven't written it yet. So I'm going to write the pseudocode. We are going to discuss the correctness of the algorithm, and we are going to discuss its time complexity. And the other thing we are going to do next week is a doubly connected edgeless data structure and how to compute the overlay of subdivisions, overlay of different maps. Okay, see you next week.